In the previous session, we have seen a quick recap on semiconductors. Now let us use that knowledge to understand a simple yet powerful electronic device, a PN junction diode. An extrinsic semiconductor with more or excess holes is a P-type material, while a semiconductor with excess electrons is an N-type material. Holes in a P-type material are called as majority carriers, while electrons are majority carriers in a N-type material. The distinction is due to doping. Why is it called a majority carrier? This is because these carriers are the ones which carry bulk of charge, implies carry majority of current. It is true that majority carriers carry bulk of current, but not 100%. So what about rest of the current? Rest of the current is carried by minority carriers. Thus, total current I is equal to current carried by majority carriers plus current carried by minority carriers. So I stands for total current and Im is the majority carrier current and Im small m is the minority carrier current. For a P-type material and N-type material, let us look at how to represent with this equation. For a P-type material, I equals Im due to holes plus Im due to electrons. For N-type material, I equals Im due to electrons plus Im minority current due to holes. The important point to note is that holes carrying current is an imaginary concept, while it is always electrons which carry charge and hence the actual current. Thus, current carried by electrons is called as the actual current. While current carried by holes is the conventional current. Now let us get to the theory of a PN junction diode. In the previous session, we learned that when a charged material is brought in contact with another charged material, there is bound to be some action. In our PN diode, we call this interesting action as diffusion. So what is diffusion? Diffusion is movement of electrons or holes from an area of higher concentration to an area of lower concentration. Thus attaining a steady state or an equilibrium state. Let us learn with an example. Consider a balloon filled with air. and this is the knot. The air is compressed and under tremendous pressure waiting to come out. Air molecules here are highly concentrated. Inside the balloon compared to outside where they are spread out and thus low concentration outside. The air molecules inside the balloon are pushing on all sides to get out. And the moment we open the knot, the air rushes from the higher concentration to lower concentration outside. Remove this knot. The air rushes from inside to outside until it reaches a steady state or equilibrium where concentration of air both inside and outside are equal. Now, similarly, when the P and N materials come together due to diffusion, holes from P region where they are excess get closer to junction to move over to N region as there is less concentration. Opposite happens in N-type material. Now, let us consider a material, a P, which has uniformly distributed holes and electrons. In this case, there is no movement of these particles and hence the material is at steady state. So consider this material where holes and electrons are uniformly distributed. These are electrons and these are holes. In this case, there is no movement of these particles and hence the material is at a steady state already. Now, consider a material where the charges are concentrated. So, this side of the material only has holes, while this side of the material only has electrons. Now, this is a non-uniformly distributed material. In this case, even without external trigger, due to thermal agitation, the charges will move to attain a steady state equilibrium. So, to attain steady state, these become a uniformly distributed material. Now, consider a PN junction which obviously has non-uniform distribution of holes and electrons. This is a PN junction. These are all holes. these are all the electrons. Obviously, this is a non-uniform distribution as holes are concentrated on the left side while electrons are concentrated on the right side. Now, due to thermal agitation, holes will move to N region while electrons will move to P region. So holes will try to move to N region and electrons will try to move to P region. Okay, so will this process of holes and electrons crossing over happen continuously? Not really. There is an interesting situation. Let us look at that. Consider holes moving from P to N region. Let us take only one hole and electron as an example. Consider this hole. This is an atom with excess hole. This is an electron. This is an atom with excess electron. Now, consider that this hole moves to this side. Once this hole crosses the junction, it will recombine with the first electron it meets, and thus the resident atom in N region, which is this one, now gets excess positive charge and becomes positively charged. So this atom is now called as an ion. So once this hole moves here, the picture looks something like this. This atom is now called as an ion. And due to hole getting attached to it, it is a positive ion. Now consider electrons moving from N to P region. So this is the P region, this is the N region. Now consider this electron moving towards this side. Now the story is similar. We get a negative ion. This is the way it works. Now there is other way to look at this process. When a hole moves from P to N region, this atom has lost that excess hole which made it positively charged, and now it becomes negative charged ion. Similarly, when the excess electron moves from N to P region, the atom becomes positive charged ion. Now here is the interesting thing. This formation of ions right at the junction slows down the diffusion process. Let us look at with a graphical representation. This is the P region, and we mentioned that the excess holes moves from here to here while the excess electrons moves from this side to this side. Now because of the ions, we see that there are a lot of negative ions formed here while there are positive ions forming on this side. Ions, which are charged particles, form an electric field like a battery. So if you see this is like a negative potential, this is a positive potential. And if you compare the diffusion process was holes was moving from this side to this side, while electrons were moving from here. Now if you look at these symbols, they both are opposite fields. Now this field, it pushes the holes and electrons to return back to their respective positions. This barrier is called as the depletion region. As now this region is depleted or lack excess holes and electrons for movement due to attraction between positive and negative ions. This barrier stays there in steady state or equilibrium conditions until some external force removes this barrier. This barrier now has its own potential energy or stored energy due to these ions stored at this junction. Hence, this is called as the barrier potential or junction potential. Barrier or junction potential. The value of this potential depends on the semiconductor material and doping material. Now, how does this potential look? So, if this is my PN junction, and if this is my barrier, now for the holes moving from P to N type, the barrier is like this. For the holes, this is the barrier potential. Now for an electron, it looks like this. Thus clearly holes and electrons have to go up the hill to cross the opposite region. It has to climb this hill, holes, while electrons have to climb this hill to cross to the other region. Does it mean that the diffusion is completely stopped due to this barrier potential? Mostly yes, unless the holes and electrons get more energy to cross the barrier. This could happen with increasing temperature. The reason being that when temperature is increased, there is lot more movement of electrons and holes due to thermal energy, and this makes it easier to climb up and cross the barrier. Now, what about the minority charge carriers? Minority carriers have exactly opposite experience. Now, if this is my PN junction, and if this is my barrier potential, and as we saw it before, for holes, the barrier looks like this, while for electrons, the barrier looks like this. The exactly opposite effect is for minority carriers. Holes in N region will see a downhill. So these are the holes, they will see a down, while it's a vice versa for electrons which are in P region, they will see a downhill. This movement of charges, also called as current, is due to electric potential, and hence this is called as drift current. Because this is due to the barrier potential. Now that drift current is opposite direction of diffusion current, and it is also not dependent on barrier voltage value. Now let us look at the equation that we mentioned in the beginning of this session. That is, total current is equal to current carried by majority carriers plus current carried by minority carriers. Now total current will become current carried by majority carriers, which is the diffusion current, plus current carried by minority carriers, which is the drift current. At steady state, a diode should be in equilibrium, which implies diffusion current and the drift currents have to be equal and in opposite direction. And hence the total current I equals to 0. This is true because the diode is unconnected diode or an unbiased current or unbiased diode, as it has no current. To get current, we need to connect a power supply to the diode. In the next section of this class, we will learn about biasing a diode and see why lower barrier potential is better.